All right, the time has come, my friends. We are into the reviews. We are going to be doing a review A, a practice test, and a review B, and then we are going to get to the test. However, all three of these things, both of the reviews and the practice test, are pretty much what the test is going to look like. It's like the questions are going to be very similar. So if you do these and do these well and you understand these, you shouldn't have any issues with the test itself. So again, you should probably have a formula sheet that you can use and ready to go. So have that handy because you probably need some of the formulas to get this stuff done. And away we go. So we begin with just a simple question about the hybrid vehicles and things like that. So there are 420 total hybrid vehicles, and we see that 105 require repairs. All right, so if there's 420 and 105 need repair, that would imply that 315 don't. All right, so this will kind of help us set up the first three questions here. Question one, in your estimate, what is the probability that a new hybrid vehicle will need a repair? So this is the probability that we have a repair out of the total. So that's 105 out of 420. Give me 1 second. Okay. The next is, in your estimate, what is the probability that a new hybrid vehicle will not need a repair? So there are 315 that don't need a repair out of 420, and that should be 0.75. Let's just check it out. Okay. And then in part C, it's either a new hybrid vehicle will or won't need a repair in the first year. What is the sample space of the problem? And what do the probabilities assigned to the sample space add up to? Okay, so two questions. One, what is the sample space? And the sample space are words, and that is everything that could potentially choose from. And so that is vehicles that need repairs and vehicles that need no repair. Okay, that is the sample space. Second part to the question, what do the probabilities assigned to that sample space add up to? Okay, so the vehicles that needed repair, vehicles that needed no repair, what do they add up to? They add up to 1. So there's two parts to that question. What is the sample space? And what do the probabilities of that sample space add to? Okay, number 2, the jar of balls. All right, so there's 8 okay, so there's 1 red, 2 green, 5 blue, grand total of 8. Okay, the first one is with replacement, the second one is with no replacement, and it's like an and then problem. So this and then that, this and then that. However, take note of when the probabilities change or don't change. The first one is a blue and then a green. So the blue is 5 out of 8, which would bump that to a 4 and a 7. But then I put it back. Okay, then I put it back, which replenishes the numbers. And then I select a green, which is now 2 out of 8. So that would be a blue, and then a green. Okay, the part B is do the same thing as part A, but don't put the ball back before selecting the second. So here we go. Let's select a blue, which is 5 out of 8, which turns that into a 4 and a 7. And now, without putting that back, I select a green. So a green would be 2 out of 7. So 5 out of 8, and then 2 out of 7. Okay, Coach Mannix is making his basketball team or something, or basketball players with A's or something like that. And so this is a problem that is, in essence, asking, what is the probability that a person is a basketball player and have an A? All right, so you can answer this one of two different ways. That can be the probability of B times the probability of A given B, or you can have the probability of A times the probability of B given A. Okay, so this is, you're going to answer the question one of these two different ways. All right, so let's see what we could potentially have. We could have the potential probability of A, probability of B, probability of A given that they're a basketball player, probability of a basketball player given that they already had an A. So you got to kind of pay attention to the second number is the population. The second number is the population. All right, so let's see what we have. Coach Mannix found that 11% of basketball players have an A. So the population is basketball players, and so the population basketball players, and then we're selecting A's from those basketball players. So the population would be basketball players, and we're selecting A's from that. 2% of the students in school are basketball players. So 2% are basketball players. Okay, so take a look at what we don't have just right from the get-go. We don't have probability of A, and we don't have the probability of B given A. So that really narrows it down on which formula we're going to be using. So this would be the probability of B times the probability of A given B. And so 0.02 times 0.11 is 0.0022. Again, how you understand what this e to the -3 thing means. If this is 2.2 e to the -3, we move the decimal place 3 places, and because it's negative, we make the number smaller. So that'd be 1, 2, 3. So that would be 0.0022. And that's how you work with the e on your calculator. Anywho, that is my answer. All right, table problems. So again, look at your formula sheet. What are the formulas that you deal with tables? And unless they use the word given, things are going to be out of 206. All right, so the first question is satisfied. So satisfied is 73. The next is very satisfied and knee surgery. So that's the intersection. So very satisfied and knee surgery. They intersect right there, and I believe that's what, 23? Where it intersects right there. So the and is the intersection, so that's 23. Last but not least is the word given. So the second piece is going to become the total. So hip surgery becomes the total. So hip surgery is 88. And the intersection is the numerator. So that's the intersection with normal, and that is what, 38 out of that 88. All right. So what are these? So we got 73 out of 206. $23 out of 206. And 38 out of 88. All right, here they give us a table of cards. And what I am doing here is these are with the word or. So the word or is A plus B minus and, or AKA the intersection. All right, so the first one is a blackjack. So it's just those two right there. Or an ace, which is those four. So we have blackjack or an ace minus the intersection. There isn't an intersection out of the total. The next is a 5. Four of those. Or a black card. There are 26 of those. Minus the intersections. There are 2 grand total in the intersections. And so this is what we have. Last but not least, we have the law of large numbers. So this is pretty much going to be a problem that is dealing with a coin, which is probably going to be a 1/2, or a die, which is usually, the answer is 1/6. You roll a die 10 times, blah, blah, blah. What is the probability, blah, 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 you got 1/6. Law of large numbers says that the probability would trend what it's supposed to be. Last but not least are going to be like tables and counting principle, which is like permutations, combinations, sort of thing. Okay, George is taking a 3-question test, multiple choice and true and false test that he didn't study for. Question 1 and 2 are true and false. So it's a 3-question test. So there's question 1, question 2, and question 3. And so question 1 are true and false. So that'll mean he has 2 options for question 1, 2 options for question 2, and the third question is a multiple choice, A, B, C, and D, which has 4 options. So how many different tests can he take or complete? And that would be 16. He will have 16 grand total different tests that he could produce. All right, so let's start with the very last option, which was the A, B, C, D, and there's going to be a grand total of 16 final answers. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, 16 grand total options. That is of question 3. That is a family of 4. So I linked those together. All right, now we're on question 2. Question true is true and false. And again, that is question 2. Those are families of 2. And then we're back to question 1, which is true and false. And that is where we start. So again, any one of these outcomes is a complete answer key to this test. It's a complete answer key to the test. Like, so for instance, this answer key would be true, false, A. So they question 1, question 2, and question 3. The first 2 are true and false. The last question is an A, B, C, or D answer. George has 4 ties, 3 shirts, and 2 pair of pants. How many different outfits can he make by choosing one of each? That's 24. Number 9, how many different ways can 12 athletes be awarded the first place, second place, and third place medal? So does the order matter in this case? Is this a president or is this a committee? Presidents, the order matters because there's a definite 1, 2, and 3. There's a definite chain of command. In a committee, there is no rhyme or reason. 1, 2, and 3 is the same thing as 3, 2, and 1. All right, so because these are medals, there's a first place medal, a second place medal, and a third place medal. Those 3 finishers, it makes a difference who's number 1 and who's number 2 and who's number 3. Yes, it does make a difference. There's definitely an order there, and so that would be a permutation. So this would be 12 permute 3. So I go 12, I go option, probability, permute 3. There's 1,320 different outcomes that could potentially result from that competition. Here we're taking a take-home exam. So there's 8, and we're grouping up 3 of them. And again, the idea is if there is 8 questions on this take-home exam, and all you have to do is do 3 of them, does it matter the order in which you do those 3 questions? Like if I did questions 2, 3, and 6, and you did questions 3, 6, and 2, would our tests be different? No, the test would not be different. The order in which you do the problems doesn't matter. The order in which you do this doesn't matter. So the order doesn't matter. That's like a committee. So it's a combination. So this would be 8 combo 3. 8 combo 3. So 8 combo 3 is 56. And I think that's the ball game. I think that's the entire test right there. Pretty sure. Yep. That's it. That's it.